waves roll on across the oceans of the world, carrying their energy as gentle, rolling motion. Waves in the ocean get their energy from the wind. As the wind rushes over the sea, it grips the surface and pulls. The surface wrinkles. The wind oscillates over the water and waves the water like a flag. As more energy goes into the wave, it gets bigger. The greater the wind, the longer it has been blowing, and the longer the fetch, or distance it has been acting over, then the larger the wave. A storm will generate a whole spectrum of different sized waves. After the fury of the storm has died away, the large waves travel on for thousands of kilometers, transferring energy through the water. If we look at how water moves in a wave, it's easy to get the wrong impression. It might look as though the water is moving forward. But if we watch this surfer waiting in a swell, we see that he stays roughly in the same position. This is because the water moves around in a circle while the energy in the wave rolls on. If we put coloured drops in a wave tank, we can see clearly how the water moves. These paths are approximately circular at the surface, elliptical halfway down, and linear on the bottom. Here we see how the movement of water molecules produces the shape of the wave. The characteristics of a wave can be described in various ways. The amplitude of a wave is the maximum displacement of the wave from the average water level. Wave height is twice the amplitude, or the distance from a wave crest to its adjacent trough. Amplitude and wave height are indicative of the energy in the wave. Smaller waves carry smaller amounts of energy. As wave size increases, so does the energy in the wave. Wavelength is the distance between two successive wave crests. In this case, 10 meters. The period is the time taken for two successive wave crests to pass a given point. In this case, it's 5 seconds. If we divide the wavelength by the period, we get the speed of the wave. Here, it's 2 meters per second. We see the logic in this formula when we apply it to real waves. In this group of ocean waves, the wavelength is approximately 20 meters. These board riders are experiencing one wave crest every 10 seconds. So the waves are travelling 20 meters in 10 seconds, or 2 meters per second. Wave speed can also be calculated using the frequency of the wave. Frequency refers to the number of waves per second. This is defined as 1 divided by the period. If we multiply frequency by wavelength, we get the speed of the wave. Again, this is simple logic. If there is one wave every 10 seconds, the frequency is 1/10 of a wave per second. The wavelength is 20 meters. So the waves are traveling 20/10 or 2 meters per second. In the open ocean, wavelength is the most important factor determining the speed of a wave. The longer the wavelength, the faster the wave will travel. One of the amazing things about waves is that they can travel through each other and come out of the encounter unscathed. While they are passing through each other, waves temporarily combine. Sometimes they reinforce each other. This is known as constructive interference. Sometimes they annul each other, cancelling each other out. This effect, known as destructive interference, is hard to see on the ocean surface because there is nothing there. It's easier to look at interference in graphic form. Here a wave with a period of 1 second is added to a wave with a period of 1.2 seconds. Where the crests of the wave are in step, they combine to create a crest that's twice as high. When a crest and a trough combine, they annul each other. The combination of the two waves results in packets or groups of waves made up of waves of different amplitude. The same thing happens in the ocean because ocean waves are often the result of 2 or 3 sources, each of which produces waves of different frequencies. These waves interfere with each other, producing groups of waves which are often referred to as sets. As a set approaches the beach, where the waves eventually break, we notice that the amplitude of the waves in the set increases to a maximum, then decreases again. Surfers use these patterns of changing wave size by waiting out the smaller waves and riding only the larger ones. When a wave strikes an obstacle, part of its energy is converted into turbulence. Much of the remaining energy is converted into a wave that reflects back off the obstacle. In shallow water, more of the wave's energy goes into turbulence. In deeper water, more energy goes into reflection. The angle of reflection of a wave is equal to the angle of incidence. In other words, the wave is reflected at the same angle at which it hits. If waves hit an obstacle at right angles, then they will be reflected at right angles. As these waves reflect, they pass through other waves, adding and subtracting as they go. If the shoreline is concave, the waves are reflected inwards roughly towards a focus. These curved waves, on the other hand, are reflections off a convex headland, seen on the left. When waves break like this, all the regular cyclic motion is destroyed. Instead of reflection, there is only turbulence. When a wave hits a jagged coastline, some of the wave motion turns into turbulence and some become scattered reflections. This way, the energy in the wave is dissipated. Waves are slowed down by shallow water. Here we can see that the waves in deep water are spaced far apart. Where the waves are slowed in shallow water, they bunch up. If a wave strikes shallow water at an angle, this bunching up causes the wave to swing around as one end slows down and drops behind. This is called refraction. We can see this effect at this beach and around this headland and on this rock platform. In this bay, the waves are refracting towards each headland. The result is that they diverge or spread outwards. The ends of each wave are the first to hit the shallow sand and slow down, while the rest of each wave continues forwards. Eventually, a curved wave diverges from the original direction. As the wave stretches, its energy is distributed more thinly and the wave diminishes. It drops suspended materials such as sand, and in this way the bay is gradually filled in and beaches are formed. Here we see the opposite effect. These waves have hit a shallow patch in the middle. As they slow down in the middle and travel faster at the sides, the waves begin to focus. The first part of the wave to hit the shallow patch slows and drops back. The rest of each wave continues and then slows down as it too hits the shallow area. Eventually, it ends up near a focal point. The wave here will have a concentration of energy greater than before. In this way, shallow reefs surrounding a headland cause waves to focus into the headland. This focused wave power eventually wears the headland away. Even after it is worn away, the waves still refract inwards. These waves are passing through a gap in a wall of rocks. Once they hit the sheltered water, they will always try to spread outwards. This is called diffraction. Once a part of the wave has been removed by a barrier, the rest of the wave is able to spread sideways and a curved wave is formed. Here it is again in this boat harbour. The end result looks similar to refraction, but diffraction occurs when a wave passes an obstacle, while refraction occurs due to the slowing of waves in shallow water. Diffraction and refraction are often seen together. These waves are swinging around the headland almost 180 degrees. This is due to diffraction in the deeper water and refraction in the shallows. The same is occurring here and here. Let's now look at what happens when a wave approaches the beach. As the wave slows, due to the shallow water, it bunches up and becomes higher and steeper. Eventually the crest starts to curve or bend and the wave falls over itself or breaks. This occurs when the height of a wave is greater than 1/7 of its wavelength. Once the wave breaks, it turns into what's called a translatory wave. It's no longer a true wave. It is only a rushing torrent of water. It's not just energy moving through the water anymore. Now the water itself is flowing towards the shore. As this rushing torrent of water flows back out again, it scours a deep channel in the sand. The current that flows in this channel is called a rip. A rip can be easily spotted because it is free of breaking waves. It is too deep for waves to break. Board riders use rips to paddle out, avoiding the breaking waves. To catch a wave when you're body surfing, you must be on the crest just as it is breaking. You will be thrown forward with the crest as it collapses. From then on, the rushing, broken water pushes you forward. As the wave fades, you will get a longer ride if you hunch your shoulders and put your head down. If you are riding a board, you are using the wave before it breaks. Because a board is streamlined, it can slide down the face of the wave. You can see that the water stays where it is while the board moves along it. Let's look closely at why a wave breaks. As the wave gets steeper, the crest keeps moving forward as part of the normal cyclic motion of the wave. But here it is shallow and there is not enough water for the wave to continue. But eventually there is not enough water and the wave collapses. At 1/16th normal speed, we can see that because the water is shallow, not enough can be drawn back to continue to support the crest. One of the main dangers when surfing large waves is being sucked back into the wave in a wipeout. The way a wave breaks depends on the slope of the seabed. A steep slope produces a dumper. These Hawaiian waves are crashing straight onto a lava reef with a very steep slope. This seabed has only a moderate slope, and a very gentle slope produces waves that spill gently. Looking at how waves break tells us something about the contours of the sea floor. This wave tells us that the water is shallower here, where the wave is breaking, than here, where the wave remains unbroken. Day after day, the waves roll in their many shapes and sizes. We've looked at how waves form, how they behave, and how they meet their end. The more we understand about them, the more they are ours to enjoy.